The manufacturing landscape is undergoing a revolutionary transformation as robots increasingly take over factory floors worldwide. What once seemed like science fiction has become an everyday reality in modern industrial facilities. From automotive assembly lines to electronics manufacturing, robots are reshaping how products are made, quality is controlled, and efficiency is achieved. The integration of robotic systems into manufacturing environments represents more than just technological advancement. It signifies a fundamental shift in how we approach production, quality control, and workplace dynamics. As factories embrace automation, they are discovering unprecedented levels of precision, speed, and consistency that human workers alone cannot achieve. This transformation is not happening overnight. It is the result of decades of technological development, falling costs of robotic systems, and increasing pressure on manufacturers to remain competitive in global markets. Companies that once relied entirely on human labor are now finding that robotic automation offers solutions to challenges ranging from labor shortages to quality inconsistencies. The modern factory floor presents a fascinating blend of human expertise and robotic precision. Workers who once performed repetitive manual tasks are now overseeing sophisticated automated systems, programming complex operations, and focusing on higher-value activities that require human judgment and creativity. This evolution represents not just a technological upgrade, but a complete reimagining of manufacturing work. Industrial robots today are far more capable than their predecessors. They can handle delicate operations with microscopic precision, lift heavy materials with consistent strength, and work continuously without fatigue. Advanced sensors allow them to adapt to variations in materials and environmental conditions, while artificial intelligence enables them to learn from experience and optimize their performance over time. The impact extends beyond individual workstations. Entire production lines are being redesigned around robotic capabilities, creating seamless workflows where materials move automatically from one process to another. Quality control systems integrated with robotic operations can detect defects in real time and make immediate corrections, eliminating waste and ensuring consistent output quality. Manufacturing companies are reporting dramatic improvements in key performance metrics. Production speeds have increased significantly, with some automated lines operating at rates impossible to achieve with human labor alone. Quality improvements are equally impressive, with defect rates dropping to near-zero levels in many automated processes. These improvements translate directly to cost savings and improved competitiveness in global markets. The financial case for robotic automation has become increasingly compelling. While initial investment costs remain significant, the return on investment is often realized within 2 to 3 years through reduced labor costs, improved quality, and increased production capacity. Many companies find that automation pays for itself even faster when considering the costs of quality issues, workplace injuries, and production delays that robots help eliminate. Different types of manufacturing benefit from robotic automation in unique ways. Automotive manufacturers use robots for welding, painting, and assembly operations that require high precision and consistency. Electronics manufacturers rely on robots for component placement and soldering operations that demand microscopic accuracy. Food processing facilities use robots for packaging and handling operations that ensure hygiene and safety standards. The automotive industry pioneered many robotic applications that are now standard across manufacturing. Assembly line robots can install components with perfect positioning every time, while welding robots create stronger and more consistent joints than traditional methods. Paint application robots ensure even coverage while minimizing waste and environmental impact. These applications have set the standard for robotic integration in other industries. Electronics manufacturing represents another frontier where robots excel. The miniaturization of electronic components requires placement accuracy measured in fractions of millimeters. Human workers simply cannot achieve the consistency needed for modern circuit board assembly. Robots equipped with vision systems can place components with perfect accuracy while maintaining the speed necessary for high-volume production. The pharmaceutical industry has embraced robotic automation for tasks requiring sterile environments and precise measurements. Robots can handle dangerous substances safely, measure ingredients with exact precision, and maintain the contamination-free conditions essential for drug manufacturing. These applications often involve life and death consequences where human error is simply unacceptable. Food and beverage manufacturing benefits from robotic systems that can work in harsh environments while maintaining hygiene standards. Robots can operate in freezing temperatures, handle hot materials, and work with caustic cleaning chemicals that would be dangerous for human workers. They also eliminate the risk of contamination that can occur with human handling of food products. Aerospace manufacturing demands the highest levels of precision and quality control. Robotic systems can machine complex components to tolerances measured in thousands of inches while maintaining the traceability required for aviation safety standards. The consistency of robotic operations ensures that every component meets the exacting specifications required for aircraft safety. The textile industry has found robots particularly valuable for handling operations that are physically demanding or repetitive. Robots can lift heavy rolls of fabric, cut materials with precise patterns, and perform sewing operations with consistent tension and spacing. These applications reduce the physical strain on workers while improving product quality and consistency. Metal fabrication and machining operations benefit from robotic systems that can handle hot materials, heavy components, and dangerous cutting operations. Robots can work continuously without the breaks required by human workers, increasing overall production capacity. They also eliminate the safety risks associated with handling sharp metal components and operating dangerous machinery. The implementation of robotic systems requires careful planning and consideration of multiple factors. Companies must evaluate their current processes, identify suitable applications for automation, and develop implementation strategies that minimize disruption to ongoing operations. This planning phase often reveals opportunities for process improvements that go beyond simple automation. Selecting appropriate robotic systems requires understanding the specific requirements of each application. Factors such as payload capacity, reach requirements, accuracy specifications, and environmental conditions all influence the choice of robotic system. Companies must also consider future needs and ensure that their robotic investments can adapt to changing production requirements. Integration of robotic systems with existing equipment and processes presents both challenges and opportunities. Modern robots can communicate with other factory systems through industrial networks, enabling coordinated operations and real-time monitoring. This connectivity allows for optimization of entire production processes rather than individual workstations. Training and workforce development become critical factors in successful robotic implementation. Workers must learn to program, operate, and maintain robotic systems. This often requires significant investment in training programs and may involve partnerships with educational institutions or robotic system suppliers. The transition from manual operations to robotic systems requires careful change management to ensure worker acceptance and successful adoption. Safety considerations are paramount when implementing robotic systems in manufacturing environments. Modern industrial robots incorporate multiple safety systems including light curtains, emergency stops, and collaborative features that allow safe interaction with human workers. Proper safety training and adherence to safety protocols are essential for preventing accidents and ensuring worker protection. Maintenance of robotic systems requires specialized knowledge and tools. Preventive maintenance programs help ensure reliable operation and minimize unexpected downtime. Many companies establish partnerships with robotic system suppliers to provide ongoing support and maintenance services. The development of internal maintenance capabilities often becomes a priority as robotic installations expand. Quality control in robotic manufacturing environments often surpasses what is achievable with human-only operations. Robots can perform consistent inspections using vision systems and sensors that detect defects invisible to human eyes. Statistical process control systems integrated with robotic operations can identify trends and variations before they result in defective products. The economics of robotic automation continue to improve as technology advances and costs decrease. Robot prices have fallen significantly while capabilities have expanded dramatically. This trend makes automation accessible to smaller manufacturers who previously could not justify the investment. Leasing and financing options also make robotic systems more accessible to companies with limited capital resources. Collaborative robots, or cobots, represent a significant development in manufacturing automation. These systems are designed to work safely alongside human workers, combining the precision and consistency of robots with human judgment and flexibility. Cobots are particularly valuable for applications requiring both automated precision and human oversight or decision-making. The programming and operation of modern robotic systems has become increasingly user-friendly. Graphical programming interfaces allow operators to create complex routines without traditional programming knowledge. Teach pendants enable operators to guide robots through motions that are then recorded and repeated automatically. These advances make robotic systems accessible to a broader range of manufacturing personnel. Artificial intelligence and machine learning are enhancing robotic capabilities in manufacturing environments. Robots can now learn from experience, optimize their performance based on data analysis, and adapt to variations in materials and processes. These intelligent systems can identify patterns in production data and suggest improvements to manufacturing processes. Vision systems have become standard components of modern manufacturing robots. Cameras and image processing software enable robots to identify parts, verify quality, and adapt to variations in positioning and orientation. Advanced vision systems can perform complex inspections and measurements that would be time-consuming and error-prone for human inspectors. Force and torque sensing capabilities allow robots to perform assembly operations that require precise control of applied forces. These systems can detect when components are properly seated, identify damaged parts, and adjust their operations based on feedback from force sensors. This capability is essential for many assembly operations where excessive force can damage components. The Internet of Things is enabling new levels of connectivity and data collection in robotic manufacturing systems. Robots can report their status, production data, and maintenance needs to central monitoring systems. This connectivity enables predictive maintenance, real-time production monitoring, and optimization of manufacturing processes based on comprehensive data analysis. Simulation software allows manufacturers to test and optimize robotic systems before installation. Virtual factory environments enable engineers to program robot operations, test different configurations, and identify potential problems without disrupting actual production. This capability significantly reduces implementation time and minimizes the risk of problems during system startup. The flexibility of modern robotic systems allows manufacturers to adapt quickly to changing product requirements. Robots can be reprogrammed for different products, and modular system designs enable reconfiguration of production lines. This flexibility is particularly valuable in industries with short product life cycles or seasonal demand variations. Energy efficiency has become an important consideration in robotic system design. Modern robots consume significantly less energy than their predecessors while delivering superior performance. Energy recovery systems can capture and reuse energy from robot motions, further reducing operating costs. These improvements contribute to both cost savings and environmental sustainability goals. The scalability of robotic systems allows manufacturers to start with small installations and expand as needs and budgets allow. Modular designs enable addition of new robots and capabilities without major system redesigns. This scalability makes robotic automation accessible to manufacturers of all sizes and allows for gradual implementation that minimizes risk and disruption. Data collection and analysis capabilities of robotic systems provide valuable insights into manufacturing processes. Production data, quality measurements, and equipment performance metrics can be analyzed to identify opportunities for improvement. This data-driven approach to manufacturing optimization often reveals benefits that extend beyond the robotic systems themselves. Remote monitoring and control capabilities enable manufacturers to oversee robotic operations from anywhere in the world. Cloud-based systems allow access to production data and system status through web browsers or mobile applications. This capability is particularly valuable for manufacturers with multiple facilities or for providing technical support to robotic installations. The integration of robotic systems with enterprise resource planning and manufacturing execution systems creates seamless information flow throughout manufacturing organizations. Production schedules, quality data, and maintenance information can be shared automatically between systems, enabling better coordination and decision-making at all levels of the organization. Cybersecurity considerations have become increasingly important as robotic systems become more connected and networked. Manufacturers must implement appropriate security measures to protect their robotic systems from cyber threats. This includes network security, access controls, and regular security updates to robotic system software. The environmental impact of robotic manufacturing systems is generally positive compared to traditional manufacturing methods. Robots typically use materials more efficiently, generate less waste, and consume less energy per unit of production. These benefits contribute to sustainability goals while also reducing operating costs. Workforce transformation in robotic manufacturing environments requires careful planning and communication. Workers need to understand how automation will affect their roles and what new opportunities may be available. Many companies find that automation creates new positions requiring higher skills while eliminating routine manual tasks. The global competitive landscape has shifted as robotic automation becomes more widespread. Manufacturers in high-wage countries can compete more effectively with low-wage countries by leveraging the cost advantages of automation. This trend is leading to some reshoring of manufacturing operations as the labor cost advantage of offshore production diminishes. Supply chain implications of robotic manufacturing include reduced dependence on labor availability and potentially shorter lead times. Automated facilities can operate continuously and are less affected by labor shortages or industrial disputes. This reliability can be a significant advantage in maintaining consistent delivery schedules to customers. The pace of technological advancement in robotics continues to accelerate. New capabilities in artificial intelligence, sensing, and actuation are constantly being developed and introduced to manufacturing applications. Manufacturers must stay informed about these developments to take advantage of new opportunities for improvement and competitive advantage. Return on investment calculations for robotic systems must consider multiple factors beyond simple labor cost savings. Improvements in quality, consistency, and customer satisfaction often provide benefits that are difficult to quantify but significant in value. Reduced warranty claims, improved customer relationships, and enhanced brand reputation are examples of these less tangible benefits. The modularity and standardization of modern robotic systems reduce the complexity of implementation and maintenance. Standardized interfaces and communication protocols allow components from different suppliers to work together seamlessly. This standardization also reduces training requirements and simplifies spare parts inventory management. Predictive maintenance capabilities of modern robotic systems help prevent unexpected downtime and reduce maintenance costs. Sensors monitor key system parameters and algorithms analyze trends to predict when maintenance will be needed. This proactive approach to maintenance maximizes system availability and minimizes disruption to production schedules. The user interfaces of robotic systems have evolved to be more intuitive and accessible to manufacturing personnel. Touchscreen displays, graphical programming environments, and simplified setup procedures reduce the technical expertise required to operate and maintain robotic systems. This accessibility broadens the pool of personnel who can work effectively with robotic systems. Advanced materials and manufacturing techniques are enabling the development of lighter, stronger, and more efficient robotic systems. Carbon fiber components, advanced alloys, and precision manufacturing techniques are producing robots with improved performance characteristics and longer service lives. These improvements enhance the value proposition of robotic automation. The integration of multiple technologies in robotic systems creates synergistic effects that exceed the sum of individual capabilities. Combining artificial intelligence, advanced sensing, precision actuation, and high-speed communication creates systems that can adapt, learn, and optimize their performance in ways that were not possible with earlier generations of automation technology. Standardization efforts in robotics are improving interoperability and reducing implementation complexity. Industry standards for communication protocols, safety systems, and programming interfaces enable better integration between components from different suppliers. These standards also reduce training requirements and simplify system maintenance and upgrade procedures. The democratization of robotic technology is making automation accessible to smaller manufacturers who previously could not justify the investment. Simplified programming tools, modular designs, and flexible financing options are removing barriers to adoption. This trend is accelerating the pace of automation adoption across all segments of manufacturing. Cloud-based robotic systems and services are emerging as alternatives to traditional on-premises installations. These systems can provide robotic capabilities through service models that reduce capital requirements and include ongoing support and updates. Cloud-based systems also enable new forms of collaboration and data sharing between manufacturing facilities. The convergence of robotics with other advanced technologies such as 3D printing, artificial intelligence, and advanced materials is creating new possibilities for manufacturing. These integrated systems can adapt production processes in real time, create customized products efficiently, and optimize resource utilization in ways that were not previously possible. Quality management systems in robotic manufacturing environments can achieve levels of control and traceability that exceed traditional manufacturing methods. Every operation can be monitored and recorded, creating comprehensive audit trails and enabling rapid identification of quality issues. This level of control is particularly valuable in regulated industries where traceability is required. The economic impact of robotic automation extends beyond individual manufacturing facilities to entire regions and industries. Communities that embrace robotic manufacturing often attract new investment and high-skilled jobs while maintaining their manufacturing base. This economic development can offset job losses in traditional manufacturing roles. Education and training programs are evolving to prepare workers for careers in robotic manufacturing environments. Technical schools, community colleges, and universities are developing curricula that combine traditional manufacturing knowledge with robotics and automation technologies. These programs are essential for building the skilled workforce needed to support continued automation adoption. The reliability and availability of modern robotic systems have improved dramatically compared to earlier generations. Mean time between failures has increased while mean time to repair has decreased, resulting in higher overall equipment effectiveness. These improvements make robotic systems more dependable and cost-effective for critical manufacturing operations. Customization capabilities of robotic systems enable manufacturers to offer greater product variety without proportional increases in cost or complexity. Robots can be programmed to handle multiple product variants on the same production line, enabling mass customization that was not economically feasible with traditional manufacturing methods. The safety record of robotic manufacturing systems continues to improve as technology advances and safety practices evolve. Modern robots incorporate multiple layers of safety protection and are designed to minimize risk to human workers. Proper implementation and adherence to safety protocols can result in safer working environments than traditional manufacturing operations. Innovation in robotic technologies is being driven by both technology suppliers and manufacturing companies. Close collaboration between robot manufacturers and end users is resulting in systems that are better suited to real-world manufacturing requirements. This collaboration also accelerates the development of new capabilities and applications. The future of manufacturing will likely see even greater integration of robotic systems with human workers, artificial intelligence, and other advanced technologies. Factories of the future may operate as fully integrated systems where robots, humans, and intelligent software work together seamlessly to optimize production, quality, and efficiency. As robotic technology continues to advance and costs continue to decrease, the adoption of automation in manufacturing will accelerate. Companies that embrace this technology early will likely gain competitive advantages that become increasingly difficult for others to match. The transformation of factory floors by robotic systems represents not just a technological evolution but a fundamental shift in how manufacturing will be conducted in the future. The success of robotic automation in manufacturing depends not just on the technology itself but on how well organizations manage the implementation process. Companies that invest in proper planning, training, and change management are more likely to realize the full benefits of their robotic systems. This human element remains critical even as automation becomes more sophisticated. Environmental regulations and sustainability goals are driving adoption of robotic systems that can operate more efficiently and generate less waste than traditional manufacturing methods. Robots can optimize material usage, reduce energy consumption, and minimize environmental impact while maintaining or improving production output and quality. The global supply chain disruptions of recent years have highlighted the value of domestic manufacturing capabilities enabled by robotic automation. Companies are discovering that automated facilities can provide greater supply chain resilience and reduce dependence on distant suppliers. This trend may accelerate the adoption of robotic manufacturing systems as a strategic advantage. Looking forward, the integration of robotic systems into manufacturing will continue to evolve and expand. New applications will be discovered, technologies will become more sophisticated, and the benefits will become even more compelling. The factories of tomorrow will bear little resemblance to those of today, as robots increasingly take over the factory floor and transform manufacturing into a high-tech, highly efficient, and highly competitive industry. The revolution is already underway, and its impact will only grow as more manufacturers recognize the transformative potential of robotic automation. Those who act now to implement these technologies will be best positioned to thrive in the automated manufacturing landscape of the future.